This section discusses the role of complex numbers in geometric algebra. Pseudo scalars. Recall that the highest dimensional objects in G3 are called pseudo scalars. They're trivectors, and they form a one-dimensional vector space. Similarly, the highest dimensional objects in G2 are called pseudoscalars. They're bivectors, and they form a one-dimensional vector space. I'm going to use the symbol G2ds to indicate the geometric algebra of a 2D subspace of Rn. They're also called pseudoscalars. They are bivectors. They form a one-dimensional vector space. I. Here's the definition. Start with an orthonormal basis E1, E2 for a two-dimensional subspace of Rn. The unit pseudoscalar of the subspace, I, is the product of the members of the orthonormal basis. The geometric product of orthogonal vectors is the same as the outer product, and so we have this, and we see that I is a bivector. Let's square it. The geometric product of orthogonal vectors anti-commutes, so I can switch the two middle members of this product at the cost of a minus sign. E1 times E1 is 1, E2, E2 is also 1, and so we have this. This unit pseudoscalar behaves as the imaginary unit, the imaginary number I, from complex number theory. And so, if we form this product, where A and B and C and D are scalars, we get this. The minus BD comes from multiplying B times I times D times I. The multiplication performs just as complex number multiplication performs. And so, multivectors of the form A plus BI are isomorphic to, have the same arithmetic structure as complex numbers. Every two-dimensional subspace of Rn has its own complex number system. Now, just a bit of language. It's a mouthful to say the 2D subspace with unit pseudoscalar I, and I'll simply say, recognizing that a 2D subspace is a plane, I'll simply say the plane I. The bivector angle I theta. Here's the definition. Start with an angle theta in a plane I. Call the bivector I theta an angle also. I theta specifies both the plane I in which it resides and its size, theta. Definition of the exponential, e to the I theta. Cosine theta plus I sine theta. U times V is equal to the length of U times the length of V times e to the I theta. I here is the unit pseudoscalar of the plane determined by U and V, and theta is the scalar angle between the two vectors. The closest analog to this in complex algebra is this formula. But here, theta 1 and theta 2 are angles measured from an arbitrarily chosen real axis in the plane, whereas in our geometric algebra formula, I and theta are both intrinsic to the two vectors. For a proof, start with the fundamental identity. and make these replacements. Replace u inner v with its definition, and replace u outer v with this. And to see that this is so, have a look at the diagram here. The plane determined by u and v is I. The I is here, and the I is here. And the area of that parallelogram is the length of u times the length of v times the sine of theta. Do a factoring, and replace cosine theta plus I sine theta with its definition, e to the I theta. This subsection is entitled Rotations, an application in which geometric algebra shines. First, we need to define a rotation by a bivector angle I theta. Here is the usual way to specify a rotation, using a rotation axis, the axis of the rotation, and the scalar angle theta, the amount of the rotation. Instead, we will often specify a rotation by a bivector angle I theta, where I is the plane orthogonal to W and theta is as before. We think of the rotation as being a rotation in a plane rather than about an axis. Rotate a vector u by a bivector angle I theta to a vector v. I want a formula which, when given u and a rotation angle I theta, gives me v. We'll take the simplest case first, that of u and v both being in the plane of rotation I. We'll start with an identity from a couple of slides back, multiply both sides by u. U squared is u dot u, which is length of u times the length of u. I'll make that substitution on the left. The length of v is equal to the length of u because u rotates to v. I'll make that substitution in one of the factors on the left. Now I've got length of u, length of v on both sides. I'll cancel it out, and I'll have my formula. To rotate a vector u by an angle I theta, I multiply by e theta, e to the I theta, on the right. Now let's consider the most general case, where u and v don't have to be in the plane of rotation. To analyze this situation, decompose u into its components orthogonal to and in the plane I, and have a look at what happens to these components individually. U perp is mapped to itself under the rotation. U parallel is mapped to u parallel e to the I theta, the formula I just proved. So we have this. I haven't proved that e to the I theta over 2 times e to the I theta over 2 is e to the I theta, but it follows from identities previously shown, and similarly for the change on the right. I also haven't proved that e to the I theta over 2 behaves this way, but again, one can show it quite easily from identities already observed. I can do a little factoring, and now I've got u in the middle, so I'll put it back together, and we have our formula. To rotate u to v through an angle I theta, multiply on the right by e to the I theta over 2, and on the left, e to the minus I theta over 2. I'm going to simply take this formula and copy it to the next slide. Here is the geometric algebra formula for rotations developed in the last slide. It's used throughout the aerospace industry and by programmers of games. Now, there are other representations of rotations. Perhaps you're familiar with orthogonal matrices. Physicists use Euler Angles, and there's a little-known formula due to Rodriguez. They all suffer serious problems. For example, if you give me the axis of rotation or the plane of rotation, together with the scalar angle of rotation, it's not so easy to write down the orthogonal matrix representing that rotation. Whereas, if you give me the axis of rotation or plane of rotation together with theta, I can immediately write down the formula above. Euler angles suffer from a phenomenon called Gimbal Lock. In addition, the geometric algebra formula is the best formula known numerically. I want to apply our formula to successive rotations in geometric algebra, one rotation after the other. So we'll start with a vector u, say, and we'll apply a rotation to it by an angle I1, theta 1. I've used the exp notation here rather than the superscript notation. We'll follow this with a rotation by a bivector angle I2, theta 2, yielding this. It's a theorem, according to Euler, that in R3 and R3 only, the two successive rotations is the same as a single rotation, say by an angle I theta. So the theorem of Euler states that this times this is equal to this for some bivector angle I theta. Let's see how this works out in a specific example. Example. I've shown Euler's theorem on the screen. The composition of rotations, one rotation followed by the other, is another rotation. Here's an example. I'll start with a rotation given by this exponential. This is a rotation in the xy plane, E1, E2, being the unit pseudoscalar of that plane. The scalar angle of rotation is 90 degrees, pi over 4 being half of that. I'll follow the rotation with a rotation in the YZ plane, again, of 90 degrees. Now I'll expand the exponentials. E to the I theta equals cosine theta plus I sine theta. Both cosine pi over 4 and sine pi over 4 are square root of 2 over 2. Squared, they become a half. And so I have this. When I multiply this out, the 1 times a half, I'll make the leading term, and the rest is the rest. Now I want a unit pseudoscalar. I have a bivector here. E1, E2, for example, is E1, E2 times 1. This is a bivector. Since I want a unit bivector, I'll divide by square root of 2, square root of 3, and I'll compensate. That's this. And once again, I have an exponential. This is the exponential representing the composition of the two rotations. On the next slide, we'll interpret it geometrically. The screen shows the result of the calculation from the last slide. What rotation does the right side represent? Well, pi over 3 is 60 degrees, so we have here a rotation of 120 degrees. But in what plane? Well, we have the plane. Its pseudo scalar is E1, E2 plus E2, E3 plus E1, E3. But it's pretty hard to see what that means geometrically. It's easier to look at the axis of rotation. In geometric algebra, that's very easy to do. I simply multiply the bivector by E3, E2, E1 on the right. We'll see later why this is so, but for now we just accept this. And if this is multiplied out, we get the axis of rotation, which you can visualize. When I lecture on geometric algebra in person, I have a large cube painted with the numbers, the faces of a die, and I carry out the composition of these two rotations to obtain this rotation. Even so, I can't see in my mind's eye why the composition of those two rotations is this. Can you?